Hi, my name is Audrey Suh, and this is my Lab 4 report on circuits. To give you a brief introduction to this lab is designed to predict the behavior of circuits both in series and parallel. The other purpose of this lab is to give us a better visualization and understanding of the structures of different types of circuits by allowing us to build the circuits ourselves and measure our own data. Some concepts covered in this lab are energy conservation, current conservation, resistors and capacitors, and circuits in series and parallel. The first part of this lab focused on charge conservation and energy conservation in series circuits. This initial system consisted of two 1.5 volt batteries, two ammeters, and two resistors. To find the predicted data for the current, I manipulated the equation V equals IR to find current and found that it predicted 0.02 amps in the system. When putting the circuit together, I found that each ammeter read 0.02 amps. When inserted backwards, the ammeter reads negative 0.02 amps because of the direction of the current. As you can see, the computed and predicted data are the same. This circuit replaces one of the ammeters with a voltmeter. The computed data, we found that the voltmeter measured 3 amps, and the ammeter measured 0 amps. The ammeter measured 0 amps because the current was not running entirely through the circuit to reach the ammeter. We used the voltmeter to measure different parts of the circuit to find their respective potential differences and found that the sum of potential differences was 0 volts. The graph to the right measures the potential against the position around the circuit, showing the various measured potential differences. When you attach the voltmeter, you alter the circuit, so why doesn't the ammeter reading change? The ammeter reading doesn't change because the voltmeter only measures the potential difference in voltage. Since the voltmeter has infinite resistance, it has no impact on the current. If we replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current changes to 0.06 amps because there is a part of the circuit in parallel which forces the current to split due to the node rule. Using the potential differences found, I calculated the resistance of each of the following circuit elements given the equation delta V over I, and found that the resistance for the 47 ohm resistor was 47.95 ohms, the resistance for the 100 ohm resistor was 102.05 ohms, and the resistance for the wire and the ammeter were each 0 ohms because there was no different potential difference across those two. The second part of the lab was RC circuits. Initially, when I connect the bulbs to the 10 ohm bulb and capacitor in series, I observed that the light produced by the 10 ohm bulb dimmed as the capacitor charged until it went out completely because the capacitor was completely charged. The more the capacitor charged, the slower the current moved until it stopped because the capacitor was completely charged. When you disconnect the battery and connect the capacitor directly to the 10 ohm bulb, what happens to the light? As the capacitor discharged, the light dimmed in the bulb until the light bulb was completely out because the capacitor was fully discharged. What happens to the current in the circuit? The current in the circuit reversed in the current in the circuit because of the orientation of the charges and then slowed to a stop as the circuit completely discharged. The time it takes in seconds to charge the 10 ohm bulb was 10.10 seconds, and the time it takes in seconds to discharge the 10 ohm bulb was 11.12 seconds. The time it takes in seconds to charge the 20 ohm bulb was 20.96 seconds, and the time it takes to discharge the 20 ohm bulb was 22.09 seconds. Something interesting to note is that the resistance is doubled, and that leads to nearly doubling the times it takes to charge and discharge the bulb. The last part of the lab was to find a graph of the natural log of the voltage difference divided by the initial voltage difference against time to find the time constant RC. The graph above is a demonstration of the natural log versus the time, and the data to the right is the data that we found. To find time constant RC, we set the natural log of voltage divided by the initial voltage difference equal to negative T over RC using the slope found earlier in the graph. The slope was negative 0.1457, and we set that equal to negative 1 over RC and found that RC was equal to 6.86 seconds. This value is close to the expected value of 6 seconds for the RC. This difference may be attributed to human error. There are some final questions for this lab, the first one being, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? If we did this lab in real life, the current of the circuits would have been lower because an actual ammeter has resistance, while the simulated ammeter did not have any resistance. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Our ideal model would predict the capacitor to reach full charge instantly, assuming there isn't a resistor in the circuit. However, in real life, the capacitor wouldn't have charged instantly because there would have been resistance without the resistor and other points of the circuits like the wires, the capacitor, and the battery. Thank you very much for listening to my presentation. I hope you enjoyed.